3,000 years ago, Persian engineers cooled buildings to 60 degrees F in deserts that reached 120 degrees F. No compressors, no electricity, no monthly bills, just water and wind working together through towers of mud brick that still function. Imagine you can do this today. No engineering degree required, no specialized tools, just physics that worked then and still works right now. And at the end of this video, you will know how this works and how you can do it yourself. Subscribe and hit the bell for more uncovering of building secrets they never taught you. Picture the ancient city of Yazd in central Iran. The year is roughly 1000 BCE. Summer temperatures exceed 115 degrees. There is no electricity. There will not be electricity for another 3,000 years. Yet, families gather in underground rooms that feel like modern air-conditioned spaces. Above these rooms rise elegant towers called badgirs, wind catchers. Some stand over 100 ft tall with multiple openings, facing different directions to capture any available breeze. These are precisely engineered machines, built from mud brick and ceramic, that have operated continuously for millennia. Here is how they work. Hot desert wind enters through the tower openings. Inside, the air passes over surfaces kept wet by water channels called qanats, underground aqueducts stretching miles into the mountains. As hot air contacts wet surfaces, the water evaporates and absorbs massive amounts of heat. The cooled air becomes denser and heavier. It falls through the tower into the living spaces below. No pumps, no fans, physics and geometry are doing the work that electricity does today. Modern measurements of functioning badgirs show interior temperatures 20 to 30 degrees F below exterior heat. Ancient Egypt constructed towers called malkafs around 1300 BCE. Same principle, different name. Every civilization in hot, dry climates independently discovered evaporative cooling. So, if engineers solved comfortable cooling 3,000 years ago, why are you paying $300 monthly to run an air conditioner? The story begins with Willis Carrier in 1902. He invented a machine to control humidity in a Brooklyn printing plant. By the 1920s, his company began marketing air conditioning for human comfort. This is where the business model becomes important. Passive cooling systems like Persian badgers require significant upfront construction cost. Then you are done. The building cools itself forever, with no ongoing expense. Mechanical air conditioning inverts this equation. The equipment costs relatively little. The system requires electricity every hour it operates, refrigerant recharges, filter replacements, and compressors that wear out every 15 to 20 years. The business model extracts payment perpetually, rather than once. Equipment manufacturers partnered with electric utilities. After World War II, American building codes specified mechanical systems. Passive cooling fit nowhere in these frameworks. Architectural schools dropped vernacular building science from curricula. By 1970, a graduate could earn a degree in architecture without ever learning that buildings had cooled themselves for millennia. But the industry could not erase the physics. And in 1997, a building in India proved ancient systems outperform modern air conditioning with data so overwhelming it could not be ignored. The Torrent Research Center in Ahmedabad covers 300,000 SQFT and contains zero mechanical cooling equipment. Massive downdraft towers rise above the structure. Water atomizes at the tower tops. Hot air enters, contacts the water mist, and cools dramatically. The building has operated for over 25 years. When exterior temperatures exceed 110 degrees, interior spaces maintain 78 to 82 degrees. Total energy reduction compared to a conventional building measures 68%. Construction cost ran about 7% higher, but within 4 years, the building had paid back its entire construction premium. Yet, drive through Phoenix or Las Vegas today and count the buildings with cooling towers. You will find almost none. Building codes remain the first obstacle. Most jurisdictions use prescriptive codes specifying equipment types rather than performance outcomes. Financing creates the second barrier. Banks assess risk based on familiarity. The expertise gap forms the third barrier. 2 generations of architects learned nothing about passive cooling in school. But these barriers are cracking. California Title 24 now provides explicit credit for passive cooling strategies. Net zero building mandates spreading through major cities make passive cooling necessary rather than optional. For residential applications in appropriate climates, whole-house evaporative coolers cost $3,000 to $7,000 installed compared to $15,000 or more for central air conditioning. Operating costs run 3 to 5 cents per hour compared to 30 to 50 cents for compressor-based cooling. These costs make a big difference for homeowners. 3,000 years ago, Persian engineers mastered cooling without electricity. For 100 years, an industry alliance buried this knowledge, not because it does not work, but because it works too well. Passive downdraft evaporative cooling works by letting hot, dry air pass through a wet medium at the top of a structure. As moisture evaporates, the air cools, and that process, evaporation, makes the air denser, so it naturally sinks down into the living space below. Start by identifying or creating a vertical shaft on the warm side of your home, ideally facing the prevailing wind. At the top, install evaporative pads or make a DIY cooling medium using thick cellulose pads, stacked burlap sacks, or coconut fiber matting. The key is a porous material with lots of surface area that can stay wet. Set up a water delivery system so the pads stay continuously moist. When hot, dry air passes through the wet pads, evaporation absorbs heat. The cooled air becomes denser, falls down the shaft, and flows into your living space through the bottom opening. Before you begin any construction, determine whether passive evaporative cooling will work in your climate. Check local humidity levels during summer months using weather data from the National Weather Service or a simple hygrometer from any hardware store for under $20. If your average summer humidity stays below 40%, you are in ideal territory. Between 40% and 60%, you will get reduced but still meaningful benefits. Above 60% humidity, evaporative cooling becomes largely ineffective, and you should consider other passive strategies such as thermal mass and night flushing instead. The simplest do-it-yourself approach involves constructing a downdraft cooler that mounts on your roof or attaches to an exterior wall. Begin by building a rectangular box approximately 2 ft wide by 2 ft deep by 4 ft tall using 3x4 in exterior plywood. Frame the interior with 2x4 lumber for rigidity and seal all joints with exterior caulk to prevent air leakage around the cooling medium. Cut an opening approximately 18 inches square in the top of the box. Install a rain cap above this opening, leaving a 6-inch gap between the cap and the box top to allow air entry while preventing rain from entering. You can fashion this cap from sheet metal bent into a simple pyramid shape, or purchase a standard chimney cap from a home improvement store. On one side of the box near the bottom, cut another 18-inch square opening. This will connect to your interior space through a duct or direct wall penetration. Install a simple damper or sliding panel over this opening so you can close the system during humid weather or winter months. Inside your box, you need a material that holds water and exposes maximum surface area to passing air. The most effective commercial option is rigid evaporative cooler pads made from cellulose, which you can purchase from HVAC suppliers for approximately $30 to $50 per panel. Install these vertically inside the box, leaving a 2-inch gap between the pads and the walls to allow air to flow around and through them. If you prefer a homemade approach, stretch burlap fabric across wooden frames, sized to fit snugly inside your box, stacking 3 or 4 of these frames with one in spacers between them. Alternatively, fill the box loosely with Excelsior wood shavings contained within hardware cloth cages, or use coconut coir matting wrapped around a wire mesh cylinder. At the top of your cooling box, install a length of 1/2 in PVC pipe, drilled with 1/8 in holes, every 2 in along its length. Cap one end and connect the other to your water supply. Position this pipe so water drips evenly across the top edge of your evaporative pads. Below the pads, install a collection pan made from galvanized sheet metal, or a plastic tray sloped slightly toward one corner, where you will install a drain fitting. Connect this drain to a 5-gallon bucket, or small reservoir positioned below the unit. For water recirculation, purchase a small submersible pond pump rated for approximately 100 gallons per hour, costing between $15 and $30 at garden centers. Place this pump in your reservoir and connect it via flexible tubing to the distribution pipe at the top. Plug the pump into an outdoor timer set to run for 15 minutes every hour during hot periods. If you want an even simpler gravity-fed system, position a covered 5-gallon bucket above the unit and run tubing from its bottom through a simple float valve salvaged from a toilet fill mechanism. The cooled air needs a clear path into your home, and stale air needs a way to exit. Cut an opening through your exterior wall directly below where you have mounted the cooling box, matching the size of the box bottom opening. Frame this penetration properly with treated lumber, and flash it carefully to prevent water intrusion. Install a short section of insulated duct connecting the box to the interior, terminating in a standard ceiling register. On the opposite side of your home, install an exhaust pathway. This can be an existing window left partially open, a dedicated exhaust vent near the ceiling, or best of all, a solar chimney, a dark painted vertical shaft on the sunny side of your home that heats up and draws air upward through natural convection. For significantly enhanced cooling, consider installing a buried air intake pipe. Dig a trench approximately 4 ft deep and 50 to 100 ft long running from a shaded area of your yard toward your home's foundation. Lay 4-in or 6-in PVC pipe in this trench sloped very slightly toward a drainage point to prevent condensation accumulation. At the far end, install a screened vertical intake above ground level with a rain cap. Connect the pipe to your home through the foundation or crawl space, terminating in a floor register in your main living area. Air drawn through this buried pipe exchanges heat with the surrounding soil, which maintains a nearly constant 55°C year-round at that depth. If you combine a buried intake pipe with a rooftop downdraft evaporative cooler, you can achieve temperature drops of 30 degrees Celsius or more below ambient conditions on hot, dry days. The ancient Persian systems worked partly because thick mud brick walls absorbed heat slowly during the day and released it at night. You can add thermal mass to your modern system by positioning the cooled air outlet so it flows across or through dense materials. Stack concrete blocks or stone pavers along interior walls in the path of the cooled air flow. Fill large clay pots with water and place them in corners of the room. Run your evaporative system during the hottest part of the day when humidity is typically lowest. In most desert climates, this means late morning through late afternoon. At night in arid climates, open windows on opposite sides of your home to flush accumulated heat and pre-cool your thermal mass for the next day. Your thick walls, concrete floors, and water containers absorb this coolness and release it gradually through the following day. Monitor your evaporative pads or homemade medium for mineral buildup from hard water. Every few weeks, remove the pads and rinse them thoroughly, or replace homemade media that has become clogged. Drain and clean your water reservoir monthly to prevent algae growth and mosquito breeding. A complete DIY rooftop downdraft cooler using the materials described above typically costs between $200 and $400. A buried ground coupled intake pipe adds another $300 if you rent a trencher or dig by hand. Compare this to operating a standard 3-ton central air conditioning system, which costs roughly 30 to 50 cents per hour in electricity. Running that system 8 hours per day through a 4-month cooling season adds approximately $300 to your annual utility bills, plus maintenance and eventual compressor failure. Before cutting holes in your walls or roof, check local building codes regarding penetrations, structural modifications, and water systems. Many jurisdictions require permits for any modification to your building envelope. Ensure any electrical components are properly rated for outdoor wet locations and connected to ground fault protected circuits. Keep water reservoirs covered to prevent mosquito breeding. You now possess the practical knowledge to build a cooling system that operates on physics rather than on perpetual electricity consumption. The principles are identical to those Persian engineers perfected 3,000 years ago. The materials are available at any hardware store. The industry made this knowledge difficult to find because buildings that cool themselves do not generate monthly revenue. But the physics never changed. Water still absorbs heat when it evaporates. Cool air still sinks. And now you know exactly how to put those principles to work. They buried this knowledge because it threatened their business model. Now you have it. If this story changed how you think about the air you breathe and the walls that surround you, please subscribe and like this video. We are uncovering the architectural secrets that were meant to be forgotten. Help us build a more sustainable future. The next blueprint for freedom will be revealed soon.